To start with, the topic is the power spectral density of the discrete PAM signals. So yesterday we saw there are various types of representation of the binary signal in the form of pulses, right? So there are return to zero formats, there are non-return to zero formats, and right, you also know that what is there is one thing which is called as the Manchester, right, or biphase, right? So those are the various options we have to convert the binary sequence into what is called as a the pulse train. Okay, now whenever we have a pulse train available, they have different power requirement, because each of those pulses put variety or various amount of powers at different frequencies, right? So because any signal has a complete every signal has its own spectrum, which are completely different from other type of the pulse. Okay, this is what we already know, so we'll look at the power spectral density. So the first part what we are going to discuss is common for each and every type of signal. That is what we are going to see. Okay, so initially I'm not going to look at any specific waveform, right? Initially what we write is general, then we look at various cases. Okay, right? So let us assume that, let us say we give a notation, say that is x of t, right? This is a pulse, right? Yesterday we plotted various pulses. Any pulse, this could be any pulse. So generally you can try to represent a pulse in the using the following equation. This is a summation, little bit of mathematics today. All right, so this is k is minus infinity to plus infinity, a amplitude, this is ak, into a pulse denoted by v of t minus k times tb. Okay, so let us assume that this be the binary sequence. So yesterday we had a binary sequence 100110011, whatever, right? So that binary sequence represented in the coded form, right? Represented in the coded format. There is a specific name for that. This is called as a line code, right? This is line code because you are converting the 1010 into the pulse format, right? That's also called as a line code in the references or the textbooks. Okay, so here we have, let's try to look at what we are writing. The v of t is nothing but the pulse shape, or I can call it as pulse shaping function, right? Depends upon RZ, NRZ, or whatever, polar, bipolar, right? Unipolar, whatever format it is. That is what is this V of t. Okay, right. Then, yeah, we know this thing. Can you tell me what is this TB? TB is the pulse duration. Okay, and we also need an AK, that is the polarity or the value, right? I can write a polarity, right? Used by pulse shape or shaping function, right? So for example, now there is a shift, right? Do you know the fundamentals in of time domain of AK is the amplitude. Okay, generally you can call this as the, I can write amplitude. Okay, now you can see this V of t is what we have defined now, right? V of t is the that particular function, which is the pulse shaping function, right? But you see, I don't have the v of t as it is in the given equation, right? You can see here it is not simply v of t, it is v of t minus k times tb, right? And k varies from minus infinity to infinity in the given equation, isn't it? So you see that what operation? What do you call that operation? Converting v of t into v of t minus k into tb is what? This concept directly taken from signals and systems. If you remember, what are the various operations that can be performed on a signal in time domain, right? So I can write I had x of t, I'm converting x of t minus t naught is what? This is shift, right? I'm shifting the signal, right? This is the shifting signal depending upon whether the t naught is positive or negative. You can say right shift or left shift, right? So tb is positive, so this is actually shifting depending upon the k value. Okay, so k value, I can see that k is negative and k is positive. So whenever k is negative, right, this becomes t plus something, so that is a left shift, right? At the same time, if k is positive, I'm getting t minus something, which is a right shift. This obviously should be represented as positive as well as negative because of one reason, right? The reason is like this. You see, okay, I'll draw a rough diagram. Okay, I don't want to spend more time over here. So let's say this is the time axis with the t equal to 0. Okay, now if I try to write a pulse like this, 0, then say high, then say low, then once again low, maybe high, okay, then one more high and low, and so on. Let's assume, so this is 0, this will be tb, this is 2 tb, this is 3 tb, maybe 4 comes here, this is minus tb, minus 2 tb, minus 3 tb, okay, and so on. You see the k value, you can see the k value here, this is 1 into tb, see this is k into tb, k is equal to 2, so this is 2 tb, k equal to 3, so 3 tb, and so on the other side I have negative, correct? Minus k is negative, minus 1 into tb, minus, and so on. All right, fine. Now, so you see that v of t itself is shifted every time, right? So if at all the pulse was here, this would have been the v of t. You see, this is shifted right by 1 unit. This is shifted right by 2 units. So I can see v of t, t minus 2 tb, t plus 2 tb if it is shifted to this side, on the other side, and so on. Correct? So you can see that there is a shifting happening. That's why the v of t, which is the original, yeah. So if this whole term becomes positive, because k is negative means the term becomes positive, right? Because minus of minus k. So that is positive. So when k is negative, the term becomes v of t plus ktb, which is left side. Okay. When k is positive, right, the term still remains negative. So v of t minus ktb is on the right side. Shift to the right side. Okay, directly taken from the signals and systems. Okay, now I see that there is a shifted version over here in the given equation, right? Multiplied by an amplitude, because this can be some a, right? A1, a, this can be fixed a, or maybe this is a or 0. You can see the ak takes different values, correct? The highest possible value can be some value, say 2.5 volts, that is ak. Otherwise it can be 0. So ak can be any value. It's an amplitude, as you told. Is it fine? Okay, so sorry, let's move further. Now, so these are the terms required to represent. Now let me tell you something in general. This is very general concept, not anything specific. Any signal x of t is given, you can convert that x of t into its PSD, power spectral density. So this means the power spectral density of this given signal x of t, which means which is x of t, I have already written that. This x of t is, in general, I can write it as, this is the notation I'm going to give, x sx of f, s indicating the power. Generally the power is denoted as s. X suffix, it denotes that it is the S of X, power of that signal X in the frequency domain. So Sx of f. What is the general equation? This is the equation. So 1 divided by the bit duration TB into, see, this is magnitude of V of f, the whole square. I'll tell you every term. Okay. So into summation, there is a n varying from minus infinity to plus infinity. I need to write a term called Ra of n into e to the power. This is minus j 2 pi 2 pi f into n into tb. Okay, this is the equation. I'll give some equation numbers so that we can refer it. So this equation is what I'm going to call as equation number 1. That is the equation of x of t, right? This equation, I'll call this as equation number 2, right? For the given x of t, its PSD is given by this equation. Now the unknown tb is known to us, so I don't have to define it. Is the bit duration. I don't know what is v of f. Okay, v of f is simply the Fourier transform. I can write ft is the Fourier transform of the predefined signal, which is v of t. Whatever pulse shaping function you have taken, right? Take its Fourier transform. Let us denote that as a v of f. Okay. And there is another term that is called as Ra of n. So normally the R is the notation given for the autocorrelation function. Okay, so Ra indicates autocorrelation of n. N is at any interval of time because discrete, right? So n equal to 1, 2, 3, 4, 5. So that discrete value is denoted by this n. So this is the, I'll write short form, autocorrelation function, ACF, of the binary data. So I'll simply write the data which we have taken. Okay, so how do you calculate that? This is the equation which we are going to use now. So there is some I variable varying from lowest possible value 0 to capital I, and there is ak into ak minus n of I, right, into the pi, which is the probability. Okay, I'll write this anyway. Ak is already defined. Okay, so pi is the probability of occurrence of the product. What is the product? There is a ak into ak minus n I. So anyway, we'll come to this point very quickly. Right? So now say I have a question like, what is the power spectral density of NRZ unipolar format? In the sense, if I want to use the NRZ unipolar format for my communication, how much power I require at different frequency? This is the question, right? So this, if you, instead of taking the signal, representing that throughout in the sense complete time domain representation taking and then calculating the power, instead of doing that, you simply take the PSD, power spectral density, and see how much power is required. This is easier. So okay, so that's why we need this calculation. Right, now we'll look at the PSD calculation one by one. So far, do you have any doubt? No. Okay, that's good. Let's proceed further. So yeah, definitely. Okay, immediately after the class I will be able to share this. Okay, so you can save it in any format and you can take printouts. All right. Okay, so this is case number 1. I want to calculate the NRZ unipolar format. Okay, that means I want to calculate this. So go back, and if you are able to recall, we have only 2 values. What are the possible values of AK? I'll write here. So this implies the AK takes only 2 values. One, yesterday we wrote 1 and 0, but now I am going to give some value because if you remember the one point which I mentioned yesterday, when it comes to the practical case, it will be a voltage. Okay, for analysis purpose, we can definitely take zeros and ones, but when it comes to the practical implementation, right, you have to have a at least one value for the high. right? So for the time being, let's say this is plus A, right? Right? Whenever it is symbol 1 or bit 1, and second one I'll try to keep it 0. Okay, low is 0 only, right? This is for symbol 0. Okay, now I need the probabilities as well, right? Because you see that previously just now we wrote pi over there, right? There is a probability term coming into picture. Practically there are varieties of probabilities that you can define, but for the analysis purpose, let's try to keep it as simple as possible. I have two probabilities, for one for 0 and one for 1, and let us assume equiprobable case, right? So you know, understand what is equiprobable, right? Zeros and ones occur with the equal and same probability. So that means this is assumption P of the AK becoming equal to 1 is equal to the probability with which the AK becomes equal to 0. It is same. So when you have two cases and both are same, they have to be half. Correct? Obviously. Right. Now, always you see our procedure is the same, irrespective of whether we are calculating the PSD of NRZ or NRZ unipolar, NRZ polar, or any other format. The procedure remains same. First, you write down what is the AK value for the given format. Then you calculate the individual probabilities. Step number 2. Step number 3 is calculate what is called as this number, this one. RA of n. Autocorrelation of the given data needs to be found in the next step. So what I do, let's calculate. This is dependent on n value. You can see that, right? This value depends on n. So let me put n equal to 0 and check what happens. Okay. Normally you have this case. Normally n comes first. So let me say n equal to 0. When n equal to 0, what happens now? You are calculating RA of 0, that is equal to summation, right? It is I. I have to decide what is capital I. I'll come back to that later. Let me write this now. So there is a AK, right? Look at the equation. I'll call this is equation number 3. Okay, look at equation number 3. AK into AK minus n. But n is 0, right? So it becomes AK into AK. That's all. Correct? So this is simply AK into AK. That means if I take AK as 0, second one is also 0. So 0 into 0 is what I'm talking about now. Okay? There is another case like AK can be 1. When AK is 1, product is AK into AK, so 1 into 1. Right? So how many total possibilities you have? You have only 2 possibilities. So the capital I value is 2 in this case. How many varieties of this thing, the product can be taken in how many ways? The total number is the upper limit of this summation. Okay, that is what is the capital I. Okay, now this becomes 2 because of the reason that I can have only 2 products, 0 into 0 or 1 into 1. Fine, is it okay? Right, so let us try to expand this to calculate this answer. So that means this is equal to the summation. Now you see I is equal to 1 to 2. I have to do this. So okay, I'll eliminate the summation. I don't want. Anyway, you understood what it is. Okay, I'll just erase that. I don't want the summation to be substituted once again. Simply right. Now you see you have AK has two values. One is plus A, one is 0. Right? So simply substitute the values of AK. Correct? So that is when I write the first term, this is A into A, AK into AK is A into A, into the probability of that product, right? There are only two cases, one is half, right? Plus second one is 0 into 0, that is also having a value half. So what happens now? So RA of 0 becomes A square divided by 2. Are you okay? Right. Now let us, I have only two symbols, right? Plus A and 0. In general, it is 1 and 0. Right. If at all you put any other value as n, say n equal to 1. Okay. When I try to put n equal to 1 or any other value of n, right, I will be getting AK into AK minus 1. Are you okay? ak into ak minus 1 means they can be equal or they can be not equal. Are you okay? Right. So how many combinations you have total? How many product 0, 0, 0, 1, 1, 0, 1, 1. So totally 4 combinations, correct? So that means all the other cases I can club into a single case, that is n not equal to 0, right? Whenever n not equal to 0, let's calculate now. That is Ra of n. This is equal to, now you write the summation. This is I till 4, right? This is simply ak into ak minus that n value, ith term into the product probability pi. Okay, so notation is fine for you, right? So let's directly write. So I write 0 into 0 into the probability. So there are 4 combinations. So this should be 1 by 4 plus 0 into 1 by 4 plus 1 into 0 into 1 by 4 plus the last, this is not 1, sorry, this is a, because our notation is a, right? Sorry, please correct. Okay, so this last one, a into 1 by 4. So that means, what is the meaning? This is equal to a square by 4. So I understood that overall, whenever you, yeah, sorry. I'm sorry. This is the one is a, sorry, my mistake. Sorry, this is 0 into a. Another one is a into 0, right? I'll update. Sorry, my mistake. That's my mistake. Just 1 second. So I'll correct that. So 0 into a, and the next one should be a into 0, right? Are you okay? Because 1 is represented as e. 0 is still 0. So 0, 0, 0, 1, 1, 0, 1, 1. Instead of 1, 1, I have a. So a square by 4. Hope this is fine. Right. So overall, this implies I can write a final answer for Ra of n. So what is the value of Ra of n? Ra of n takes these values, either a square by 2 when n equal to 0, or it is a square by 4 whenever n is not equal to 0. Fine. Call this by some number, maybe I think it is 4. Okay, let's proceed further. Right? Any doubt so far? No. Good. Okay, now let's come to the pulse shaping function, right? That is the V of t. All right, because let me write in this way, because we are considering the NRZ unipolar, right? So for NRZ unipolar, what is the V of t? V of t can be either positive or 0, right? Amplitude is, anyway, you know the amplitude. Either you put a over there, it becomes a into that function, or 0 into a 0 into that function. Either a into the function gives you the function as answer, a into the function as answer, otherwise it becomes 0. So what is the v of t to which you multiply by ak? That is, it's a rectangular pulse, correct? Are you okay? So whenever my symbol is 1, what you are passing? You are passing this function, right? You are multiplying by, this is 1 into the amplitude a. That's why it comes as a as the answer for symbol 1. Whenever it is this, you still have the same function, but you multiply by 0. That's why it becomes simply 0, correct? Are you okay? So the function which you are using over there is the rectangular function. Correct? It's a rectangular pulse. So how do you represent, what is the equation? Recall from, I think we studied in signals and systems. Once again, I'm directly taking from that. So that is represented as a rect of t by tb. So the denominator tb says the width of the pulse is tb. Total width is tb. Okay, I'll write only one of them now, because this is the rectangular pulse which we are talking. So this is the amplitude. Amplitude is 1. So this is the function rect of t by tb. So that means it is centered at 0. On the left hand side, it goes halfway. So tb by 2. Right side, it is plus tb by 2. Now you see the total width is tb. This is the tb which is there in the denominator of the inside the bracket. Okay, amplitude 1. right? Amplitude is 1. So what is the equation if you want to write? This is 1, right? If magnitude of t is less than TB by 2, correct? So magnitude is less between this, minus TB by 2 to plus TB by 2. The signals and system way of writing this. Okay, this is 0 else. Okay, hope you have seen something similar to this in signals and systems. Okay, right. This is one point. Now the actual part comes into picture. This is one part of the definition of the V of t. Now, are you able to recall what is its Fourier representation? That is more important, right? If I have V of t, which is equal to the rect of t by tb, what happens, how its Fourier transform looks like? Do you remember? No, no problem, right? So we already have studied. So anyway, we are not deriving that. I'll directly write the answer. So the rect function has Fourier transform denoted by TB into, it's a sinc function, right? Sinc is a standard function. Do you remember how it looks like? Sine theta by theta is a sinc function. Okay, so that is sinc of, it's a frequency domain. So F into TB. All right, very standard. Just remember this. I'll highlight this. Okay, so just to indicate that this is important. Okay, right. So this is important. Now we are going to use this. So we got so many equations to remember now. Let me denote this also by n. Okay, I think 4, this is fifth one. So now let me go back. So equation 5 gives you V of f. Equation number 4 gives you what is Ra of n, right? I can substitute that V of f and the Ra of n in equation number 2, because equation number 2 has only two unknowns, right? 1 by TB, TB is predefined. V of f whole square, I can put the V of f here, just now we calculate, right? We have that answer. Ra of n, yes, we have that value. Just now, previous to that, we calculated that. E to the power minus j 2 pi, something like e to the minus j theta, very standard. Okay, that's a Fourier representation. Converting something into a Fourier means you simply multiply by e to the power minus j omega t. Correct? That is there here. So equation number 2 is fundamentally you are converting something onto the frequency domain by squaring the magnitude. You can see V of f whole square. Right? So we put everything back into that equation. So this implies, right? I'm actually writing the equation number 2 once again now, just to make sure that we substitute everything. So equation number 2 gives, what is there on the left hand side? It is Sx of f, right? That is equal to 1 by Tb magnitude V of f whole square into, there is a summation with n as a variable of from minus infinity to plus infinity, the Ra of n into e to the power minus j 2 pi f frequency domain, n is that which varies from minus infinity to infinity into the TB, that is a bit duration. Okay, so this is what I have in the equation 2. Now let me substitute, because I calculated every value, I just have to substitute now. So this is equal to, the TB remains as it is, 1 by TB, right? V of f, I think we have a value for V of f with us, right? I can simply substitute the V of f as it is. So what is that? V of f. Okay, before that, I think I know I can make one step here, which brings more clarity into this. Let's keep the V of f as it is. Okay, this is V of f whole square. I will split this summation, because the summation, the Ra of n has two values. One when it is 0, so that is simply Ra of 0, correct? Plus all the other values when n not equal to 0. That means I can write still another summation, that is n minus infinity, but n not equal to 0 till n equal to plus infinity. This still remains the same, Ra of n into e to the power minus j 2 pi f n into TB. Hope this is fine. Okay, so let's go further. Now we substitute, because everything what we have, we can substitute here. So this means I have 1 by TB as it is. So look at this. I have V of f, just now we calculated. So if you see that value, it is TB into sinc function of f into capital TB. So I have to square it because magnitude function. Simply you write that is TB square into, this is sinc function, so sinc square of f into TB. Okay, then substitute. What is RA of 0? Do you remember? A square by 2, right? Plus RA of n is a constant. That has nothing to do with the summation. So let me take it out directly. I'll write the RA of n, which is a constant, that is a square by 4. I can write it outside. Then let me write that summation. Okay, so that summation is nothing but sum of n is equal to minus infinity to plus infinity, n is not equal to 0 into only the exponential term remains, e to the power minus j 2 pi f n to tb. Okay, now, okay, the whole substitution is over. Only now the mathematics kicks in, right? I just have to solve this using any method I know in mathematics. You can simplify to get the answer. Okay, so now no more communication, no more DSP, nothing, right? Only mathematics, pure mathematics. Okay, suggest me a method to simplify this. Specifically, anyway, this can be multiplied, no problem. I will get an answer, but I need to eliminate that summation sum, right? Can you think of something? There actually it is not a simple summation. If at all it was something like minus infinity to infinity, definitely I might have some formula to be substituted. There is a specific condition which says n is not equal to 0. That means this is a not a very continuous summation. There is a break in the middle, correct? Because n, it says that n cannot be equal to 0. We don't have any formula, right, which skips some terms, right? Like n cannot be equal to a specific value a, but the summation is still from minus infinity to infinity. Such things we don't have a formula. Okay, the formula we have, whatever formula we have, is for the continuous summation, like minus infinity to come continuously till plus infinity, maybe you have. So how do you add the term n equal to 0? You can add. If you add, you have to subtract because actual term does not have that. So when n equal to 0, this n becomes equal to 0, correct? That n equal to 0 means e to the power 0. What is the value? 1, right? So what I do, I'll add 1 so that this summation can be completely from minus infinity to plus infinity, but I need to subtract. So minus 1. So plus 1 minus 1 will cancel that. The whole effect is nullified. Are you okay? So out of which, anyway, let's do some mathematics now. So this is TB. I can write sinc square F times TB into, let's write the a square by 2 plus, I still have the a square by 4 outside, but now you see, because of the modifications we did, we can write it as n equal to minus infinity to plus infinity complete, right? E to the power minus j 2 pi f n tb minus 1. All right. Yes. Now I can multiply and I can try to, definitely I can try to simplify. So that is equal to, let's multiply. For the first multiplication gives you a square into TB divided by 2 times sinc square f TB. All right. What's the second multiplication? There is a minus 1 over there, isn't it? Can I try to simplify that? A square TB by 4. Okay, I'll come back. Just check this. See, there is a term n not equal to 0. Correct? You understood this step? Plus 1 minus 1. Okay. Now you see, in the next step, I'll change the color for your this thing. You see the summation. I eliminated n not equal to 0 from that. Right? So the plus 1 goes inside this because n equal to 0 is included, right? In the summation. Are you okay? I hope that is okay. Now, So we'll write, we'll be able to write like this. Okay, now, so that means, so let us try to multiply and write this, right? So first term is fine for you. Okay, let's write the second term. When you write the second term, I have a square. This is plus, and I write a square into TB whole divided by 4. I still have the sync square function f into TB into that summation. Okay, so this summation is n is equal to minus one, sorry, minus infinity to plus infinity e to the power minus j 2 pi f n TB minus 1. All right. Now, anyway, we need to have this. This is still inside the bracket. Let's put the bracket. Right. Now, you see, we have one specific representation over here. That is, now this is actually a very standard summation. So I'll hold on to this. So I think this is equation number 6. Okay. So this is equation number 6. Now we have one very standard formula. This is again taken from mathematics, wherein we discuss various types of Poisson's distributions and formulas. From there, you can write one thing, but this term, that is the summation n is equal to minus infinity to plus infinity. If you have the e to the power minus j 2 pi f n TB minus 1. Okay, this can be simply replaced as 1 by TB into summation, change the variable, maybe m is equal to minus infinity to plus infinity. It is a delta function, delta of, right, impulse function of f minus m divided by TB. Okay, so this is actually, this has a name for it. This is equation 7. This is called as the Poisson's sum. Right? So I'm using this. So I will put 7 in 6. Put it back. Right? So when you put the 7 in 6, I'll show 6 as well so that the substitution becomes simple for us. So on the left hand side, I still have Sx of f. So Sx of f, it's a square TB divided by 4, right? Okay. One second, one second. I think I missed a square. Yeah, sorry, sorry. Sorry, there is a small mistake in my calculation. What I do, I will multiply this summation plus 1 and minus 1. Okay, let's make a small change. There is a minus 1 here. I should not include. I think Poisson sum does not include that. Let me go back. Please correct. I'll do the correction now. Okay, so this minus 1 should be kept outside by mistake. I'll rewrite. Sorry. So summation here into this a square TB by 4 into that minus 1. Sorry. Okay. Are you fine with that? Because that there is a minus 1. I need this bracket is not applying to that because plus 1 minus 1 is not for that summation, right? I simply added a 1 and subtracted, isn't it? So I'll just make a correction. So this bracket is not applicable for the, it's only till here. Okay. Now a square by 4 gets multiplied to this minus 1 as well. All right. So I have a bracket like this. Okay, now you see the difference. I'll erase this part so that the Poisson sum I can rewrite later. I'll add up the next part. So the next part is minus, this is a square tb by 4, minus because there is a minus 1, I'm multiplying. Okay, a square tb by 4 into the sinc square f into tb. Are you okay with this now? No, this is the correct. So this is 6. So now I will actually substitute only for this, that there is another version of the what you call Poisson sum. Okay, so but we have this. If I have n is equal to minus infinity to plus infinity, e to the power minus j 2 pi f n into tb can be simply replaced as 1 by tb into the summation. This is m is minus infinity to plus infinity, another uh, discrete impulse function in the frequency domain, f minus m divided by tb. Now you see, as m changes, delta function shifts to left and right in the frequency domain. Are you okay? M changes because m is minus infinity to plus infinity. Similar to our previous case, simply compare this with, right, the v of t minus k times t, right? So the tb, instead of multiplying, I divide k by tb. So instead of f, I have t. The domain, the x-axis is not t now, it is f. Okay. M you change. M is negative means f plus m by tb, right? So that should be the left shift. When m is positive, it still remains delta of f minus m by tb, which is the right shift. Correct? So the summation of this e to the power actually generates shifted version of the delta functions or the impulse. That's the meaning. Okay, so let's substitute that. So now actually you can see this and this term, these two can be clubbed because their the functions are same, only the coefficients are different. A square tb by 2 minus a square tb by 4 is actually a square tb into 1 by 2 minus 1 by 4. So half minus quarter is quarter, 1 by 4 remains, isn't it? Are you okay? So this denominator becomes a 4 now, right? That's the only term after clubbing these two. So this is into sinc square f into tb. That's my first term. Are you okay? And the second term, whatever we have earlier, I'll write that with the new update. That is after substituting this equation number 7 back in 6. So this is a square tb divided by 4. The sinc square still exists. Sinc square of f tb into the term, that is 1 by tb into the summation, that is m is my variable from minus infinity to plus infinity, into delta of f minus m divided by t. Okay, now so I need to look at something more, right? Because it's not a straightforward way. If I directly substitute something for this, we don't understand. Okay, for that purpose, I have to write what is called as a one graph, right? So one graph containing sinc square function and the second one containing this. We'll draw that. Okay, we'll draw two graphs, right? So which one? Minus a square tb by 4. This part, last one. Is it? That's what you are asking? Actually, that is simplified, right? You see, you can add these two, right? They are same. You club them together. Yeah. So there is a 1 by 2 here, minus 1 by 4. That is equal to 1 by 4. That 1 by 4 I have written. Is it okay? Okay, fine. Right. So now, in order to simplify this further, I need a help of a graph. Without that, I cannot. Even if I write, there will be question in your mind. How come? So just to answer that, I'll directly uh, plot two graphs. Okay, one is the sync square function. So let's try to draw the sync square function first. So the sync square function, you see, there is one very peculiar relationship between time and frequency. What is the relationship between time and frequency? If TB is the time, what is the equivalent frequency of TB? My simple question is very simple. If I give you a time duration T, how do you convert that time into the frequency is my question. I can reframe the question. What is the relationship between time and frequency? Very simple. I give you a time period of sine wave. How do you convert that into the frequency of the sine wave? How do you calculate using the time period? How do you calculate its frequency? Is my question. Very simple. Nothing complicated. Huh. 1 by f, correct? So they are inverses of each other, isn't it? So now if I know that my signal is having a duration of TB. Every symbol is of duration TB. TB2, TB3, TB4, TB. At those points, they are actually they are changing their values. This is what you know from the given signal. Now my question is that what should be their corresponding frequencies? It should be 1 by TB, double of that, 2 by TB, 3 by TB, and so on, isn't it? Are you okay? So this is now it's not time axis. I'm in the frequency domain. Correct? You see why I'm saying I'm in frequency, because you see the variable here, sync square of f into t. See which domain you are in the frequency domain. Correct? So the axis tick values, whatever I am writing here, they should be the frequencies. Are you okay? So I'm not writing TBs now. I have to write 1 by TBs over here. So this is frequency 0. This is frequency equal to 1 by TB. Frequency equal to 2 divided by, oh, not 2 TB, 2 divided by TB. Because TB, 1 by TB is my frequency. Keep multiplying the frequencies. 1 by TB, 2 by TB. So this should be 3 divided by TB, and so I will not write. Similarly, minus 1 by TB, minus 2 by TB, minus 3 by TB, and so on. Okay, so now the sync function is what I'm trying to plot. Okay, so what you're trying to plot here is the sync square of f into TB. Okay, so it has a highest value of 1. So if you somewhere you might have seen this. Okay, so this is how it looks like. It starts from highest, comes to a lowest, then another secondary maximum, but not as high as the previous one, and it keeps on reducing. Okay, so this is the shape of the sync square function. Okay, both side I'm expecting it to be sorry, it should be equal. So at least I'll try to manage that. Okay, kindly bear me with my drawing. Okay, so it cannot be very accurate. If I try to make it accurate, it wastes our time. So I will stick to whatever I am able to draw. Okay, like this, and keeps reducing. Okay, hope the shape is fine for you. It actually goes till infinity. So the signal is from minus infinity to plus infinity, which indicates your pulse has infinite frequency. Correct? Because f-axis extends from minus infinity to plus infinity, means that your signal has all the frequencies from minus infinity to plus infinity. At those points, 1 by dB to 2 by dB, minus 1 by dB, they are 0. That's fine. Those frequencies do not exist. But other than that, all the frequencies do exist. Correct? That is the sync square. Okay. Now what I did, I plotted this. I need a product of this with this, right? I just have to take a product. right? So I don't need the TB to be considered because this TB cancels ultimately. All right. Okay, fine. So now I'll plot this delta function. You know this already. What is this? The delta of f getting shifted to 1 by TB, 2 by TB, 3 by TB, and so on. Correct? Right? Because m is minus infinity to plus infinity. This is very easy to plot. I don't have to struggle at all. Let me try to draw. So this is what I need to plot now. This is still on the f-axis, but you see, I will write the function that I'm plotting with a different color. So, yeah. So this is the function. Okay, so if I try to draw the pulse train, this should look like this. At every that 1 by TB also I have this because m is equal to how much? You see m value becoming equal to 1, m equal to 2, delta function shifted, m equal to 3, delta function shifted, m equal to 4, shifted, m equal to 5, right? M equal to minus 1, m equal to minus 2. I know I have to do this all the way from minus infinity to plus infinity. Are you okay? The magnitude is 1. So this is 0. Yeah, magnitude is 1 because you see, I'm just plotting this function. So what is the magnitude? Delta. Whatever is the magnitude of delta is the amplitude. Correct. What is the magnitude of delta function? We already have studied that in signals and system. Delta of n has amplitude always 1. Okay. But its position might change depending upon whether you have a shift or not. So if there is a f minus f naught, in this case f naught is equal to m by tb. So there is a shift. So it shifts according to the m value. Okay, so what are the shifts? The similar shifts, 2 by TB, there could be 3 by TB and so on. I'll write few of the negatives also, minus 1 by TB. So this is minus 2 by TB and so on. Okay, this is also going all the way from minus infinity to plus infinity. Now, can you answer my question? My question is, what is this product? Sinc square into this. That is this function into this function. What is the answer? Can you answer? Look at the graph and answer. It's a point by point multiplication. Rectangular pulse, how? It's a point by point. You see, I'll use a red already. I'll change the color. Okay, I'll change to blue. You see, what is the product in this range here and here? What is the product? This into that. You see, this is 0, right? I don't have a value. So 0 into anything is 0. Okay, fine. I don't have a signal answer coming in this blue colored marked region on the graph. Okay, I'll move further. I have a value like 1 here, but what is the value here at this point? 0, right? Because it comes. So there is no product here. This into this is 0. 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 But do you have any answer or completely 0? Now you have to tell me. Only one sample, correct? Only one sample, right? That is also at f equal to 0, correct? Frequency 0. How do you write that answer? So if I want to take the product, so what is the answer now? That is equal to, how do I write? I cannot write simply 1 because answer is not 1 everywhere. What is the notation? It's only this arrow mark, correct? So what is the answer? Answer is only this arrow, correct? At 0 on the frequency axis, if you write this is nothing but the delta of f, isn't it? It's delta of f function. So I can go back and I can replace that whole product in my previous equation. I'll call this is equation number 8, right? Using this, the graph I can write. Therefore, 8 becomes equal to, now I'm trying to write my final answer. Okay, I'm coming very close to my final answer. So that is the Sx of f is equal to, so the first term you can see in equation 8, I don't have to simplify that. That's already in the most simple format. So I'll write as it is. That is a squared tb by 4. So there is a tb, okay? This is capital T. A square tb by 4 into the sinc square of f into tb, okay? Plus only the second term, there is a simplification, right? What is a constant? Constant is only a square by 4, correct? So a square by 4 into delta function, that's all, correct? A square by 4 into the delta of f. So this is the final answer that indicates how much power is present at each of the frequency if you use the NRZ unipolar format. So I will show you the one graph. Okay, you may have to draw this graph as an answer if a question is asked. Okay, so this is the final answer and corresponding graph. So what I'm plotting here is f into tb, because you see the axis, horizontal axis, whatever we are plotting is sinc square f tb. Okay, so we are writing f into tb as the what do you call this? So because you see f is equal to 1 by tb, right? I multiply by that by tb means what? My frequency becomes 1. Next one will be 2 by tb. So next value into tb means what? My x-axis becomes 1, 2, 3, 4 now. That's all. That's why. Just to simplify that, we are multiplying. Okay. Otherwise, definitely you can write 1 by tb, 2 by tb, etc. No issue. Okay. So whatever you feel comfortable, you can use it, right? That is still valid. Okay. I'll write first few values. This is at 0, at 1, at 2, and so on. Now I can see that there is a delta function, right? And it is delta of f. Whenever you say this is delta of f, where it should be marked? It should be marked at 0, right? At 0, right? Location 0 and magnitude 1, isn't it? Right. So since my axis is this, I'll mark this. Okay, so make it exactly at 0. Okay, so this is the delta function which we are writing. Okay, so that will have, this is a square by 4 its magnitude, because delta of f is getting multiplied by that. Then if at all it is simply sinc square, right, the magnitude is 1, but it is a square tb by 4. All right, so that will be, that is where it starts. It will start from somewhere here, it will come down, it has to reach 0 and then goes up, then comes down, then goes up, and so on. So what is this magnitude? This magnitude is equal to a square tb by 4. Okay, so the delta function has an amplitude a square by 4, and this highest point of the sinc function, because that is a different function I have to add, so that function has a magnitude highest value equal to a square tb by 4, right? I am simply converting this into this, that's all, this equation into the graph. Okay, so I hope this is clear. So this itself is Sx of f for the non-return to 0 unipolar form. That's how we do the calculation.